We're going to look at tangent lines, and in order to get started with that, we're actually going to start with something called secant lines. What we're looking at is a curve that I've called f, and a point on the curve that I'm going to refer to as an anchor point, and a corresponding point on the x-axis. What we're going to do is we're going to connect lines between our anchor point and other points on the curve. So to the right, I've got a blue, green, and purple, and to the left, I've got an orange and brown. And just for visual reference, I'm going to put corresponding points on the x-axis. As I go from blue to green to purple, what you can see is that the x-coordinates of these points are approaching the x-coordinate of our anchor point, the black one, from the right. And then when I go from brown to orange, again, we're approaching the x-coordinate of the anchor point from the left. As I draw each of these lines here that connects 2 points on the curve, what we're seeing is that you can see why I'm calling it an anchor point, right? They all intersect at this black point. And the slope of the blue line is more than the slope of the green line, which is more than the slope of the purple line. The slopes are getting shallower, right? And then when we move to the left of the black point, the slope of the the brown line is really shallow, and then the slope of the orange line is actually increasing. And what you can see is, if you imagine these points getting closer and closer to the black point from the right and from the left, then you can imagine that there's a trend here, and there's a line that kind of would sit between, say, the orange and the purple one, that would just kind of touch the graph in only one spot, right? And here it is. It's this black one here. So the slopes of the blue and the green and the purple are eventually becoming the slope of the black line as my point gets closer and closer to the black point from the right. And then the slopes for the the brown and the orange ones are getting closer and closer to the slope of the black line as I move toward the black point from the left. All of these lines of various colors that are not black intersect the curve at more than one point, and these are all called secant lines. And we can characterize a secant line as a line that intersects a curve more than once. And you can see that's characteristic of all of these various colored lines that I drew. Now you might point out, well, the black one touches the curve more than once. That's because of how the graph bends on itself, right? But by definition, a secant line is going to intersect more than once. If we did this same process with a point way over here, then I might be able to come up with a line here that only intersects the curve one time, right? So we demand that a secant line has to intersect more than once. A tangent line may or may not, but I'm less concerned with what happens out here than I am what happens near the point of interest, what I've been calling the anchor point. And so we're going to say that a tangent line is a line that touches a curve. If we look at this blue line here, you can see that if this was a knife and this was actually a physical object, the curve, then if I slice along the blue line here, then I'm going to cut off a piece of the curve, right? And that's actually what secant means. It's from a Latin word which means to cut. And tangent is from a Latin word that means to touch. Has nothing to do with the trigonometric tangent. It's just a repetition of words that don't mean anything that's related to each other. Wow, when good sentences go bad. All right, what I'm going to do is I'm going to label the x-coordinate of the anchor point A, I guess for anchor point. No, it's just to identify it as having a specific value. And then the blue one I'm going to call A plus H. And using function notation here, the blue point would then be a plus h, f of a plus h. Those would be its coordinates. And then the black one we're going to say is a, f of a. So we can say that the slope of the blue secant line is, well, rise over run, right? F of a plus h minus f of a divided by h, because the a's subtract out, right? Or another way to think of it is, if this truly is rise over run, then the run here has a value of h. Now here's the thing, by varying what h is, we can get different points on the curve. And if I know the value of h, then I can come up with a slope between 2 points on the curve using this same expression. That's kind of cool. And of course, h can be a positive or negative number. Now what you're seeing happening here as I go from blue to green to purple is that H is getting smaller, right? And then if I go from brown to orange, again, H is getting smaller. Now I'm going to actually make a change to what I've written here. I'm going to say that this is M sub SEC. And what I'm saying is this is the slope of a secant line. And I don't care if this is referring to the blue one, the green one, the purple one, whatever it is. But that's the expression for the slope of a secant line. The slope of the tangent line, well, it's going to look the same. It's f of a plus h minus f of a divided by h as h tends to 0. So if we were to let h get smaller and smaller and smaller and then tend to 0, then we would obtain the slope of this tangent line, either from the left or from the right. This allows us to write the equation of the tangent line. The equation of the tangent line to f at the point a f of a is y minus f of a is equal to f of a plus h minus f of a divided by h times the quantity of x minus a. What we've really done is fleshed out y minus y1 is equal to m times x minus x1, right? Point slope form for the equation of a line, as h tends to 0.